You! Yes, you! Come on! Help us, help us!
Help! Click
It's
it!
too high!
Click
Come
it,
on.
please!
Imagine turning the ocean into both a source of fresh water and clean energy, yet today, over 2 billion people still live in regions facing severe water stress.
To address water scarcity, many coastal regions rely on seawater desalination. What is it exactly? It is the process of removing salt and other minerals from water, making it suitable for human consumption, irrigation, or industrial use. How does desalination work? So first, seawater is collected from the ocean through an intake system. Large filters remove debris such as sand, seaweed, and small marine organisms. Next, the water goes through a pre-treatment stage, where additional filters and chemicals are used to remove smaller particles and microorganisms. After pre-treatment, the water enters the reverse osmosis system. Here, powerful pumps push the seawater through a semi-permeable membrane at a very high pressure. These membranes allow water molecules to pass through but block dissolved salts and minerals.
Desalination currently provides fresh water for more than 300 million people globally, making it a crucial technology for many coastal and arid regions where natural freshwater sources are limited. Unfortunately, desalination typically consumes between 3 to 10 kilowatt of energy for every cubic meter of freshwater produced. As a result, the process releases large volumes of concentrated brine that is usually discharged back into the ocean. It is extremely energy intensive. In fact, global desalination plants consume over 200 terawatt hours of electricity every year. This leads to a broader global issue known as the energy trilemma, which refers to the challenge of balancing energy security, affordability, and sustainability. Although renewable energy is growing worldwide, the current growth rate is still not fast enough to meet global climate targets. Another major environmental concern is brine waste. This brine disposal can harm marine ecosystems as the high salinity and chemical residues can disrupt marine organisms and reduce oxygen levels in seawater, including ocean acidification, which threatens marine biodiversity and ocean health.
Brine. What is it exactly? Brine is the highly concentrated salt water that remains after fresh water is produced during the desalination process. For every 1 liter of fresh water generated, up to 1.5 of brine can be discharged. This brine contains high concentration of dissolved ions, such as calcium. However, brine also contains unused chemical potential energy due to its high salt concentration. This energy, also called blue energy, can be captured to generate electricity up to 2 terawatts if properly harnessed.
Due to this, we would like to introduce Saltwatt. Our project proposes an integrated energy recovery system for desalination plants. This system combines 3 main components. The first one is enhanced pressure recovery using ERD systems, which could recover approximately 60% of the energy used. The second system is reverse electrodialysis for salinity gradient power generation. Lastly, it's sustainable electrode materials derived from used batteries. This is an image of a standard desalination plant across the globe, with high-pressure brine exiting the membranes that still contain significant energy. Our system improves the efficiency by utilizing a new innovative system in energy recovery devices, allowing more of this pressure energy to be transferred back into the incoming seawater stream. This reduces the load on high-pressure pumps and lowers the total electricity consumption of the plant. Even a 5% improvement in pressure recovery efficiency can save hundreds of thousands of kilowatt hours per year in a medium-scale desalination facility.
The second part of our system uses reverse electrodialysis, a technology that converts the difference in salt concentration into electricity. When 2 solutions with different salinity levels are separated by ion exchange membranes, sodium and chloride ions naturally move from the concentrated solution to the diluted solution. This ion movement creates an electrical potential that can be harvested through electrodes. In our system, the concentrated brine from desalination acts as the high salinity source, while incoming seawater or diluted streams acts as the low salinity source. By stacking multiple membranes together, we can generate a continuous electrical current. Although the power output of each membrane is small, the system can operate continuously and sustainably, turning previously wasted salinity gradients into useful electricity.
A unique aspect of our project is the use of recycled battery materials in the electrochemical components. Every year, the world produces over 50 million tons of electronic waste, much of which contains discarded batteries. These batteries contain materials such as carbon rods and metal casings that can be repurposed as electrodes. By reusing these materials, our design reduces the need for new resources while also lowering production costs and supporting circular economy principles.
By integrating these technologies, our system improves the overall sustainability of desalination. Our analysis suggests that energy generation could reduce energy use by approximately 5 to 6%, saving more than 700 megawatt hours of electricity annually. Beyond financial saving, our system helps lower the carbon footprint of desalination plant. Therefore, because some ions are redistributed during the process, the remaining brine becomes slightly less concentrated before being released back into the ocean, helping minimize salinity shock to the marine ecosystem and support long-term marine sustainability. Finally, by incorporating recycled battery materials, our design promotes a circular energy approach while also addressing the global challenge of e-waste management.
However, there are still some limitations to consider. First, the system may require a high initial infrastructure cost. Secondly, the efficiency of the system depends on the salinity gradient between different water streams. And finally, in tropical environments, biofouling can occur, where organisms and marine organisms accumulate on membranes and surface.
Also, looking forward, this concept could be further expanded in several ways. First, it could support disaster resilience. The centralized energy recovery system could provide small but reliable backup electricity for emergency lighting, communication systems, or water purification. Second, AI-assisted optimization could be introduced to improve system performance.
As we conclude our presentation, we would like to highlight how our project Saltwatt contributes to the UN SDG, which are SDG 6, 7, 13, and 14. Saltwatt helps make freshwater production more efficient and sustainable. Secondly, our system contributes to the development of innovative low-carbon energy technology. Thirdly, Saltwatt helps reduce the energy demand of desalination facilities, which in turn lowers their carbon footprint and supports global efforts to mitigate climate change. Finally, Saltwatt promotes more responsible management of desalination waste and contributes to protecting the marine biodiversity.
Hello. Hi. Well, I guess this is the end of our presentation. Yeah, the laptop is dying. Well, I guess that concludes our innovation idea for this time. Hopefully, we can use this project to move to a sustainable future.
Yes, we will see you soon.
Good morning, good evening, and good night.
Bye.